equal to 1 by d. Okay. Right. So the question may be asked like this. Explain the structure for FIR, decimator and interpolator and the direct form structure of 0 to 1 decimator is shown like this. So this is 0 to 1 decimator. 0 to 1 decimator. Okay. So this is h of n can be written like this: x of n z power minus 1 into h of 1. So this is h of 0, h of 1 into z power minus 1, h of 2 into z power minus 2, h of n minus 1, z of n minus 1. Okay. All will be cascaded. So, and after that, this is the down sampler, so that f dash equal 1 by f into 1 by t. Okay, right? So is equivalent to decimator down sampler. After that, we have the h of 1 down sampler, h of 0, then z power minus 1 into down sampler into h of 1. Okay, z of minus 2 into down sampler into h of 2. Okay, like this. So these two are identical. Direct form structure of d to 1 decimator, 0 to 1 decimator. So x of n is the input, y of d is the output, f is sampling frequency, and d is the sampling factor. Okay, so the relationship between input and output of the filter is given by yd equal to sigma n equal to 0 to n minus 1 h of n into x of bd minus n. Okay, so the direct form structure of 1 to I interpolator is shown in figure 2. Okay, 1 to I interpolator. That is figure 2 means this is 1 to I interpolator. Okay, so that is x of n equal to input, y of d is the output, f is sampling frequency, and I is the sampling rate expansion factor. So in direct form structure of 1 to I interpolator, the output is obtained by increasing original sampling frequency by a sampling rate expansion factor 1, factor I, that is interpolator upsampler, and this is followed by anti-imaging filter. So f equal to if, and here f equal to if, right? So this can be drawn like this: I h of 0 into this is if z power minus 1, z power minus 2 into h of 2, z power minus 2 into h of 3, z power minus 4 into h of 4, like this. So this is y of t is equal to if, f is equal to if. So this can be drawn like this. So these two are identical. So this is direct form structure of 1 to I interpolator. So next one is draw the direct form structure of IIR filter for D to 1 decimator. So the difference equation for an IIR system is given by y of n equal to sigma k equal to 1 to d d1 ak into y of n minus k plus sigma k equal to 0 to n minus 1 into bk into x of n minus k. This is the form difference equation. This is the difference equation form. So for this, we will apply Z transform on both sides. So Z transform of y of n equal Z transform of this entire expression. So Z transform of y of n is nothing but y of z. Okay, y of z. So y of z equal to Z transform of this one, that is sigma k equal to 1 to d1 ak into z power minus k into y of z plus sigma k equal to 0 to n minus 1 bk into z power minus k into x of z, right? So y of z is taken as common, y of z into 1 minus sigma k equal to 1 to d1 ak into z power minus k is equal to sigma k equal to 0 to n minus 1 bk into z power minus k into x of z. So that h of z will become, okay, h of z will become y of z by x of z, or it is equal to y of z is y of z by x of z, that is sigma k equal to 0 to n minus 1 bk into z power minus k by 1 minus sigma k equal to 0 into d1 0 to d1 ak into z power minus k. So this is the direct form structure of IIR filter for 0 to d to 1 decimator. Okay, this will be derived from the difference equation of IIR system. Okay, where h of z is called transfer function of an IIR filter. Okay, so sigma k equal to 0 to n minus 1 bk and z power minus k is nothing but numerator polynomial of h of z, and 1 minus sigma k equal to 1 to D1 AK into Z power minus K is nothing but the denominator polynomial of H of Z. So the order of N and D, numerator and denominator polynomials are same, and D1 equal to N minus 1, right? If D1 is N minus 1, the order of the numerator polynomial and denominator polynomial both are same. Okay, the direct form structure of an IAR filter for D21 decimator is shown in figure. So that is already discussed. Okay, so this is the basic structure. So from this we will draw this one. So this is direct form structure of an IAR filter for D21 decimator. So for this one we have drawn the structure, direct form structure. Okay, next explain polyphase decomposition process. Explain polyphase decomposition process. What is polyphase decomposition process? The computational complexity of FR filter is reduced by polyphase decomposition. What for this is used? The computational complexity of FR filter is reduced. Okay. The computational complexity of FR filter is reduced by polyphase decomposition. Let us consider H of n is the impulse response of the filter. Okay, then H of Z is sigma n equal to 0 to n minus 1, H of n into Z power minus n, Z power minus n, H of Z. So H of Z is equal to H of 0 plus H of 1 into Z power minus 1 plus H of 2 into Z power minus 2 plus H of 3 into Z power minus 3, like that. So I'll write H of Z as H of 0 into Z power minus 2 into H of 2 plus even harmonics and odd harmonics, like that. We'll write even harmonics and odd harmonics. So plus Z4 minus 1 into H of 1 plus Z4 minus 3 into H of 3, like that. Okay. Now we'll take the type 1. Type 1 is polyphase decomposition is represented as H of Z equal to E naught of Z square plus Z4 minus 1 into E1 of Z square. Okay, E naught of Z square plus Z4 minus 1 into E1 of Z square. This is type 1 polyphase decomposition representation, where E naught of Z square and E1 of Z square are called polyphase components. Okay, we are writing the polyphase decomposition in terms of polyphase components. Okay, polyphase components are E naught of Z square and E1 of Z square. Equation 1 represents two branch polyphase decomposition. Okay, two branch polyphase decomposition. If type 1 polyphase decomposition has 0 branches, then it is given as D branches, non D branches. Decimation. Decimation stands for D. That's why if type 1 for polyphase decomposition has D branches, then it is given as H of Z equals sigma K equal to 0 to D minus 1. Okay, D minus 1, Z4 minus K into EK of Z power D. Okay, EK of Z power D. Okay, this can be drawn like this. Okay, X of n and this is y of d, x of e naught of z square, e1 of z square into z power minus 1 is identical equal to h of z. Okay, so this is structure of type 1 polyphase decomposition. Structure of polyphase decomposition, e naught into z square plus z power minus 1 into z power minus e1 into z square is equal to h of z, right? So coming to the type 2 polyphase decomposition, which is represented as h of z is equal to z power minus 1 into r naught of z square plus r1 into r1 of z square. So h of z equal to z power minus 1 into r naught of z square plus r1 of z square, where r naught of z square and r1 of z square are polyphase components in type 2. Equation 2 represents two branch polyphase composition, whereas type 1 is represented as two branch polyphase decomposition. Okay. Okay. So it is also represents the two branch polyphase, two branch polyphase decomposition. So if the type 2 polyphase decomposition has D branches, then it is given as H of Z is equal to sigma I equal to 0 to d minus 1 z of minus d minus I minus 1 into Ri of z power d. Ri of z power d. So where Ri of z power d is equal to E of d minus I minus I into z power d for I equal to 0, 1, 2 up to d minus 1. So it can be represented as structure of type 2 polyphase decomposition is represented as x of n is equal to r naught into z square into z power minus 1 plus r1 into z square, which is identical to h of z. Okay, this is type 2 polyphase decomposition structure. So this is structure of type 2 polyphase. So here we have type 1 and type 2 polyphase decomposition structure. This one mathematical will represent the mathematical representation of type 1 and type 2 and draw the structure of type 1 polyphase decomposition and the structure of type 2 polyphase decomposition. Right? Okay. Right. Then we'll see the polyphase decomposition of IIR system with the transfer function. Okay, obtain the polyphase decomposition of the IIR system with the transfer function h of z is equal to 1 minus 5 into z power minus 1 by 1 plus 4 into z power minus 1. So type 1 polyphase decomposition is given by h of z is equal to E naught z square plus z power minus 1 into E1 of z square. Okay, E naught of z square and E1 of z square are polyphase components. Okay. What is the given transfer function? H of z is equal to 1 minus 5 z power minus 1 by 1 plus 4 z power minus 1. Okay, taking rationalizing, then it will become 1 minus 5 into z power minus 1 by 1, 1 plus 4 into z power minus 1 into 1 minus 4 into z power minus 1 by 1 minus 4 into z power minus 1, right? So by multiplying the numerators and this is a plus b d minus b, that is a square minus b square, so that it will become 1 minus 9 z power minus 1 plus 20 z power minus 2 by 1 minus 16 z power minus 2, right? So it is equal to 1 plus 20 z power minus 2 by 1 minus 16 z power minus 2 plus z power minus 1 into minus 9 by 1 minus, it is in the form of h of z. Okay, that is equation number 2. Okay, by comparing or equating equations 1 and 2, we get E naught of z square is equal to 1 plus 20 into z power minus 2 by 1 minus 16 into z power minus 2 and E1 of z square z power 2 is equal to minus 9 by 1 minus 16 into z power minus 2. This is the polyphase decomposition. Obtain the polyphase decomposition of IIR system with transfer function, given transfer function. Next, obtain the polyphase structure of the filter with the transfer function h of z is equal to 1 minus 3 z power minus 1 by 1 plus 4 z power minus 1. In the same manner, we can do this one. Okay, the same manner, and we will obtain the E naught of z square and E1 of z square. Okay, so rationalizing, and we will get 1 minus 7 into z power minus 1 into 12 z power minus 2 by 1 minus 16 z power minus 2. Okay, and h of z equal to 1 plus 12 z power minus 2 by 1 minus 16 z power minus 2 plus z power minus 1 is taken as common into 7 by 1 minus 16 z power minus 2. So E naught of z square is 1 plus 12 z power minus 2 by 1 minus 16 z power minus 2 and E1 of z square is minus 7 by 1 minus 16 z power minus 2, right? Okay, next, this is about the polyphase components of the type 1 and type 2, type 1 system. Okay, type 1 and type 2 systems. Next, we'll see the applications. Applications of, discuss the applications of multi-rate digital signal processing. Okay, applications of multi-rate signal processing. So first one is implementation of narrow band low pass filter. Implementation of narrow band low pass filter. So the characteristics of narrow band low pass filter are narrow pass band and narrow transition band. The narrow band LPF is susceptible to finite word length effects since the order of filter is high. This type of filter requires more number of filter coefficients and very high memory locations. To avoid this, a low pass filter is implemented in multi-rate approach. Okay, so if you take the decimator and interpolator, so here, so upsampler and downsampler both are there. So upsampler before the downsampler low pass filter, that is anti-aliasing filter, will be introduced in decimation process, and in interpolation process after the upsampler we will introduce the anti-imaging filter. Anti-imaging filter. These two are suppressed with low pass. These two are combined in a low pass filter. Why? Because more number of filter portions and very high memory location. This requires more number of filter coefficients and very high memory level. To avoid this, the LPF is introduced. Okay, so here H one of n and H2 of n are low pass filters, right? X1 of n is the input sequence, H2 Y1 of n is the output sequence, right? Okay, let F is the sampling frequency of X1 of n, then the new sampling rate. In the new sampling rate, f dash becomes f dash equal to f dash equal to f dash equal to f by m. F by m. First of all, upsampler shown in figure 1 is used to obtain the actual sampling frequency of filtered data, that is y1 of n is equal to f. Okay, and then the following conditions must be satisfied. What are those following conditions? Okay, see, the following conditions must be satisfied. So first one is low pass filters H1 of n and H2 of n are identical. Their pass band and stop band ripples should be delta P by delta P and delta S. Okay. Next, implementation of digital filter banks. Okay. Filter banks are usually classified into two types. They are analysis filter bank and synthesis filter bank. Okay. Filter banks are two types: analysis filter bank and synthesis filter bank. Oh, so what is meant by analysis filter bank? So M channel, if you take M channel analysis filter bank, that can be drawn like this: X1 object, this is a V0 object, these are the outputs. So H0 object, these are the filters. H0 object, H1 object, H of M minus 1 object, and this is downsampler follower. So it will give output V0 object, V1 object, Vm minus 1 object. So this is M channel analysis filter bank. Okay. So X of Z at Z equal to E for geometry input sequence, and frequency range W omega equal to 0 to pi 0 to pi. H0 of Z is equal to low pass filter, H1 of Z minus H of M minus 2 of Z equal to band pass filter, and Hm minus 1 of Z is high pass filter. Okay, in between these two we have the band pass filter. So this is a analysis filter bank. This is about the analysis filter bank. Coming to the synthesis filter bank, output to input. Okay, so V0 of Z to sampler. So the G0 of Z, G1 of Z, Gm minus 1 of Z, these are all the filters. All will be added so that we'll get the output. So the V0 of Z, V1 of Z, V2 of Z, right? And Vm minus 1 of Z are input to interpolator. Inputs fed to interpolator. The output of each interpolator are applied to various synthesis filters. Okay, GK of Z. The outputs of all synthesis filters are combined hence we get the output signal X cap of Z. Okay, so that is G0 of Z is low pass filter, and G1 of Z minus Gm minus 2 of Z is band pass filter, and Gm minus 1 of Z is a high pass filter. In between low pass filter and high pass filter, we have the band pass filter. This is about the synthesis filter bank, right? Synthesis filter bank. Next, we will do some problems. A multi-rate system is as shown below. Find the relation between X of n and Y of n, right? So, this is the given system. X of n, the down sampler, up sampler. This is also down sampler and up sampler. This is form. And these two are added so that we will get the output Y of n, right? So, after down sampling, we get the see, this is the down sampler. After down sampling, V of n is X of 2n. X of 2n, right? X of 2n. If we upsample V of n, here, V of n, we get Vu of n is equal to X of 2n by L. Here L value is 2, X of 2n by 2. That is equal to X of n for n is equal to n equal to 0 plus or minus 2 plus or minus 4, etc. Okay, right? Then it is equal to 0 otherwise. Okay. Right. If we delay X of n and then downsample, we get we delay X of n and then downsample. Here we are delaying X of n. Okay. Then omega of n or W of n equal to X of 2n minus 2. Okay. X of 2n minus 2. Right. So and upsampler it is equal to X of 2n minus 2 by 2. Okay. Right. So this is X of 2n minus 2 and X of 2n minus is equal to X of n minus 1 for n equal to 0 plus or minus 2 plus or minus 4, etc. And it is 0 otherwise. Okay. Then y of n equal to by adding these two, vu of n minus 1 plus w of n. Okay. Vu of n minus 1. So here this is vu of n. After this is vu of n minus 1. Right. Then Vu of n is equal to Vu of n equal to x of 0, n is 0, if n is 2, is x of 2, and if n is 4, is 4. So n is 4, this is it. So 4, etc. Like this we can write. So it is 0 otherwise. It is 0, if it is 1, it is 0. If it is 2, it is 2, it is x of 2. If it is 3, it is 0. Like that V of n minus 1, V of n minus 1 is equal to n minus 1 is equal to 0 of 0 like this x of 0 x of 2 0 etc. The same manner W of n is this one, W of n is it is 0 x of minus 1, okay, 0 like this. So W of n plus W of n minus 1, adding these two, x of minus 1 plus x of 0 x of 1 x of 2 x of 3 etc. So this is x of minus 1 x of 0 x of 1 x of 2 x of 3. So y of n is equal to x of n minus 1 is x of n minus 1. the solution. Like this, we can do the problem. So we have to make it accept and manage. The next one is for the multi-rate system shown below. Develop an expression for the output y of n equal to y of n as a function of the input x of n. So, so this is the given system. Y of n x of n is the upsampler, downsampler, and this is the upsampler. So we can write this one as 5. If 10 can be written as 5 into 2, or 2 into 5. Okay? 2 into 5. Downsampler 2 into 5. Okay, or it is identical to downsampler 2, downsampler 5, upsampler 3, downsampler 4, and then upsampler 2. Okay, so this is x of n equal to downsampler 2. These 2 will be cancelled.